Hello and welcome everyone. Thank you for joining yet another exciting webinar on working with Microsoft's microservices and Kubernetes, all what you need to know. So I am Jonathan on behalf of the Explorer Dev community hosting this webinar sponsored by Gapstars in collaboration with Kubernetes Sri Lanka community and Colombo Docker community, as well as shout out to the DevOps Sri Lankan community. So let me do a quick check. If you can hear my audio clearly, please do type yes on the chat before we move on. Thanks. So meanwhile, let me continue just to remind everyone that this series is all part of the Explorer webinar series that we've been conducting for the last few months. And last webinar on Docker, we asked some of our participants what's the best topic that you'd like to follow up with. And no doubt the participants responded with asking if we could talk on Kubernetes. And here we are on another session with this webinar, diving into Kubernetes and also looking at the microservices aspect of it. So without any further ado, I just remind everyone that you're muted as of now, and we'd like you to post any questions on the chat anytime during the session. And I think Nilesh has very much obliged to take on the go the questions that we've required for. So let me not spend too much time, but to introduce our speaker today. Very welcome Nilesh Jayanandana. He's the principal software architect and certified Kubernetes administrator, always sporting the Kubernetes, and kind of being the enthusiast as always. So welcome to you, Nilesh. Thanks for joining us, and may I probably hand over to you. Stop sharing my screen right now. Over to you, Nilesh.
Yeah. Hi. Thanks, Jonathan. Let me share my screen. Okay. Can all of you see my screen?
Yes.
Okay. So thanks, Jonathan, for the intro. So today we are going to start talking about working with microservices and Kubernetes. So before we start, so one thing that we need to do is that there's another meetup that's happening by Kubernetes Sri Lanka. Unfortunately, the two clashed. So if there are any advanced users who are interested in running Kubernetes, Windows containers, etc., just head over to the other meetup where another speaker would be talking about Windows containers and how to run them on Kubernetes. In this particular session, what we are going to do is we are going to just touch base on the introductions. I'm going to see what are microservices, how containers fit into the scenario, then what are the new problems that arrived with the containers, and then how Kubernetes came in as a solution, why Kubernetes, and then I'm going to touch base on the architecture of Kubernetes and a couple of key concepts on Kubernetes like pods, deployments, and services. And then I'm going to give you a few pointers on how to run Kubernetes in production according to my experience. Then I'm going to do a small demo if the time permits to run a simple deployment and a service in the cloud in Kubernetes. And then I'm going to just on the next steps, I'm just going to talk about how as beginners you can start learning Kubernetes and start working with Kubernetes. So that's the agenda. So let us start with a brief towards microservices. So Gapstars, this Explorer webinar would, on the next webinar, they will definitely be doing about microservices. So you will get more in-depth detail about microservices in the next webinar. So in this one, I'm just going to touch base on the basics. So as you can see in the diagram here, uh, and on the left side, it's monolithic architecture where the user interface, business logic, data access layer, everything bundled into one application. Like if you take an ERP application, then the UI, then the employee management part, HR, finance, all of those things would be on the one project, one application. We call that a monolith. Whereas under the microservice architecture, those are segregated into smaller units. So the HR management would be one microservice, uh, employee management would be another, finance would be another, payroll could be another, likewise. And then they can have their separate databases as well, depending on their use cases. They all can share the same database, or they can have their. It's very flexible. So the advantages of microservices basically is it's easier to scale. So what I mean by easier to scale is basically like imagine that your shipping management system gets request about 1,000 requests per second, whereas the employee management system is getting about 5 requests or 10 requests per second. So if this is a monolith, the entire application you will have to scale because all of these are in the monolith scenario. Hypothetically, to run monolith, say you have a minimum requirement of 2 GB of RAM. So you need to sort of by applications of 2 GB to handle such a load. But in this scenario, this is segregated into smaller pieces. So like employee management system can stay as it is because it's getting only 5 to 10 requests per second. But the shipping system that's getting 1,000 requests per second, you can scale that one only to however much you like to support the demand. And that will help you immensely. And then in this scenario, hypothetically, we can say that we have allocated about 200 megabytes for employee management system, and again 500 megabytes for the shipping system. So when we scale it, it's going to be multiplications of 500 rather than in this scenario, scaling the entire system. You can just pick a small component and scale it according to your needs. Again, another thing was easier to build and maintain. When it comes to a monolith, there are thousands of codes and there are a lot of things in a monolith. It's very hard to maintain as the monolith becomes, as you add more features, as there are a lot of complexities and a lot of code to manage. But with microservices, it's very easy because these will be smaller projects. The lines of code is smaller and the margin for error is very less. And productivity and speed, that is also another thing. When we are working with a monolith, there are a lot of things to consider. Planning, when you insert a new feature, you had to think how it affect the other modules, etc., etc. But if it's microservice, you just create a project and you write what you need, and it's very simple. And the flexibility around technology, like say in a company, there are multiple teams in a company, in an enterprise. So we can't expect all the people in the company to be experts in Java or be experts in Go or Node.js or PHP. Okay, different people are experts in different languages. So we can have small teams where one team with people specializing in Python, another team specializing in Go, another team specializing in Node.js, and then then give them the service and they will write it on the language that they prefer. It's very flexible. Yeah, I touched base on cross-functional teams as well. So yeah, and then here's what Jeff Bezos has to say: if you can't feed a team with 2 pizzas, it's too large, unless of course you have a fat person in the team. Yeah. So where does containers fit to this scenario? So I believe last webinar it was about containers, and my friend Kasun did a good job there. So I hope everybody attended that. If not, Jonathan will put the link for for the link on containers, explaining what Docker and containers are. So I'm just going to give a brief intro here as well, because it is sort of necessary for us to speak about Kubernetes. So looking at the comic here, you can say that if everything breaks in production, what happens? Like your QA and everybody would look at you, and all you have to say is just like Bart says here, it works on my machine. but that's not an answer. You can't ship your machine. So that's where Docker came in. So Docker is the ideal solution to the problem of how to run your software reliably between environments, from one computing environment to another. So containers, as a quick recap. So the difference between virtual machines and containers, I think most of you know this. It's going to be boring for you. I'm just going to touch bases very, very quickly. So under VMs, you have infrastructure, you have hypervisor, you have an operating system. Now this operating system doesn't know that it is a virtual machine. So it thinks that it is completely isolated, and it thinks that it is the whole machine. It doesn't know about hypervisor and infrastructure. Same here, same here. And then we run the app on here, we run the app here, we run the app here. You might be wondering, like some people, if it's a PHP application, I know that a lot of people would run multiple PHP apps on the same operating system. But no, we are not talking stuff like that. Imagine you have 3 applications, 3 microservices, one written in Python 2 and another written in Python 3. How hard is it to run it on the same machine? Normally, as a best practice, so yeah, it's going to be hard, because Python 2 libraries and Python 3 libraries conflict with each other, unless there are workarounds, obviously, like if virtual env and etc. But hypothetically, if that is not there, then what would happen is that you cannot run 2 applications here because there are conflicting dependencies. That's why you have to sort of switch into 2 virtual machines. Now the problem with running 2 virtual machines is, now you see the guest operating system here. Now to run an Ubuntu or a CentOS or whatever an operating system, there's a minimum requirement. That means to run the basic services in that particular operating system, you need around, hypothetically, let's say it requires around 1 GB of RAM and 1 CPU just to run its services, right? That's already gone. If this is a 4 GB RAM VM, already 1 GB is gone for the operating system for its services. You only have 3 GB remaining, right? So in this scenario, from the hypervisor, if you are creating 3 virtual machines, in this particular scenario, you are wasting 3 GB of RAM just for an operating system, which is, doing the same thing on all 3 virtual machines. Now, when it comes to containers, it's a different scenario. Now you have infrastructure, you don't have a hypervisor, you have an operating system. So under that operating system, you have the Docker engine. And then on top of that, we have this concept called containers. So now what the containers do is, these containers share the dependencies and share the host operating system libraries. Now in this scenario, there's only one host operating system, which means the system is more effective, efficient. You're only wasting, or you're only giving away 1 GB of RAM to this operating system, whereas you're giving away 3 GB of RAM to 3 operating systems here. And app B and app A, these are completely isolated, and this app A and app B have their own file system, etc., etc. So they would ideally be running as isolated processes, and they can't talk with each other because we are running on the same operating system. But the required level of isolation and everything is there for this app A to think that it is running on its own VM, and app B to think that it is running on its own VM, sort of a thing. So this helped us a lot, because in a microservices world, if you have around hundreds of microservices, it's going to be cumbersome for us to have hundreds of virtual machines and manage all of those applications in those. Rather than that, we can have 2 or 3, because say one microservice is around, say it requires around 200 megabytes of RAM, and we can't create a virtual machine with 200 megabytes of RAM. I don't know. I haven't seen such virtual machines, but I believe, I don't know. So that's the case. So containers actually, that's how containers fit into the picture here with microservices. It allows us to, have spin up a couple of machines and then, run these containers, run multiple applications in a single VM on an isolated manner. So this is how microservices look like when it comes to VMs. It's like this. Per VM, we have an app, but with microservices, with microservices and Docker on a single operating system, we can run multiple applications with multiple dependencies, etc., etc. So yeah, up to now, you can give me a shout out if you have any questions. The next slide, we are going to talk about the problems that comes with microservices and Docker. So, there are any questions?
Yeah, I think there was one on the OS that you have touched already. Uh,
Okay.
Maybe, yeah, if there's anything, we'll take off on the Q&A as we go.
Yeah. So one person said, "What if we would want full control up to the OS level? Is Docker still good fit compared to the VM?" Well, if you want to control at the OS level, there's this concept called root containers. When you run a root container, you can control OS level work, but it's not advised. It's not advisable. Yeah, we'll discuss. I think what's best is that at the end of the session we'll discuss all the questions at once. Yeah, I'll just go on with the slides and then we can touch base on those. Um, okay, so the new problems that came up with Docker and microservices. With Docker CLI, you probably would have seen on the last webinar. It allows you to manage the lifecycle of containers manually. So if you have one microservice, you can easily type Docker run, and you can run this container. There's this thing called Docker Compose. I don't know whether this was covered. So what Docker Compose allows us to do is like sometimes the applications are multi-containers, right? An application would have a front end, a service, a backend, and a database. So all of that together, we call it an application. So Docker Compose allows you to run all three at once and manage them at once. It's just run one container at once and that's it. You cannot do scaling and etc. It's just run three containers. That's the end of it. That's the end. So is that really enough? It's not, because when it comes to microservices, if you take an ERP application, there's going to be thousands of microservices. Hypothetically, let's say that you write 100 services, but you're scaling these things. You're scaling them horizontally as requests come and etc. So in a scenario like that, you're going to end up with thousands of containers, and then managing them through CLI manually is going to be very cumbersome. You cannot really do that. A human being cannot do that. Managing thousands of containers via Docker CLI manually. So that is why we need orchestration. So that's one of the main reasons why I needed orchestration. Other than that, the other reasons for us to have orchestrator is basically like we would have a bunch of virtual machines, and then we need an orchestrator to sort of say, right, I have a bunch of microservices to run. The orchestrator needs to do the scheduling and resource allocation. What I mean by this is it needs to look at the availability of all the nodes available to it and see what are the available resources, like what are the available CPU and memory of each and every node. And then it has to decide where my container should be scheduled. Because if we were to do this manually, then we had to look at all the VMs, we had to see the usage patterns there, and then we had to see how much of requests each and every container is required to run minimum requests, and then we had to do these things manually. It's going to be, it's not feasible to do. One person or people cannot do that. That's why orchestrators exist. So using an orchestrator, all we had to do is tell orchestrator, look orchestrator, I have my Java application. This Java application requires 1 GB of RAM to run. Uh, and I want this scale to 3 replicas. And then the orchestrator would say, okay, I'll do this. And then it's going to look at all the VMs that are allocated this particular orchestrator. It's going to see where that Java container would fit in best. And then it would do the scheduling there, and then it would just take care of it. And if the Java crashes, Java app crashes, the orchestrator would, you know, it would constantly monitor it and restart the container if required. Scaling again, we can easily tell the orchestrator, my Java application, I want it scaled to 5 instances, and the orchestrator would do that. Service discovery again. Now, when we have multiple containers, etc., now we need to speak to these containers, ideally through a protocol like HTTP or gRPC. So when we're talking to these, now the service needs to find these things. We call this service discovery. So because our application cannot, we don't know the IPs because these containers are dynamically created and dynamically deleted, right? So we need something like a service discovery mechanism so that we would have a static IP to sort of call these service calls, and then through that static IP, it's automatically the service discovery should happen, and then the traffic should get routed to all the containers that that belongs to a particular service. So we would touch base this in the future on this slide in the future. And then manage network and access, track state of the application, availability of the application. There are a lot of things the orchestrator do that makes things easier for us, and that is exactly why we need orchestrators. So when it comes to orchestrators, Kubernetes isn't the only kid in town. There's Docker Swarm, there's Apache Mesos, there's Nomad by HashiCorp. There's a few out there. Is the hype, and a lot of people, there's a huge community for Kubernetes. The reason being that earlier it was I think it was a race between Kubernetes, Docker Swarm, and Mesos. So when Docker introduced the concept of containers, what happened was the concept of containers was already there. What Docker did was basically it made it easier for us to use containers, and then they provided these use cases so that we can easily do create images, run as containers, etc. But the concept of containers was there from long ago. It's based on the Linux kernel. Containers as a concept is basically from Linux kernel namespaces and C groups. So containers existed before Docker. Docker just enabled us to do it. So when Docker was launched, I think in 2013 at PyConf, I don't remember, PythonConf. Yeah, so it took the community by storm, and it changed DevOps as we know it. But Google at that time, they also had, like, their systems were also running on this container concept. They had this container tool called Let Me Contain That For You, LMTCY. So and then Google had another tool called Borg to actually orchestrate these containers created by LMTCY. And then Google was going to open source LMTCY, but before Google did that, Docker came in and Docker open source Docker. I think Docker was called .cloud by then. Then what happened was, now Google knew that, people would now, Google wanted people to start using containers, get accustomed to it. And then Google knew that there would come a time when people start using containers, there would need the people would need the orchestration of containers. The need for orchestration would come. And then Google carefully targeted to release Borg, redubbed as Kubernetes, to serve this purpose. And then they donated it to CNCF. Now Docker people also knew this, and then they developed a tool called Docker Swarm. And Apache also knew this. Apache had Mesos and etc. But however, how Kubernetes won the race was basically because the Borg project was there on Google under production, handling production containers, production workloads for so many years before it was rebranded as Kubernetes and open sourced, which means that it was already production ready. It was production tested at Google level. Whereas Docker Swarm, Apache Mesos, etc., wasn't production ready. It wasn't stable. It was very new, and there wasn't much support for it. So that is why people sort of rallied around Kubernetes, and then a huge community developed around Kubernetes, and people started developing and contributing to more and more features as people wanted. And that is how Kubernetes has become big as of today. And just Docker Swarm, Mesos, everything else just uh, fell behind the race. But I'd say no bad by HashiCorp is pretty good. Like Kubernetes is sort of heavy, but if you have just smaller scenarios, Nomad by HashiCorp is also pretty good. All right, so I already explained why Kubernetes is. Uh, yeah, so now I'm going to speak about, from this slide onwards, I'm going to be touch basing on Kubernetes architecture, uh, how Kubernetes work, and a few key concepts. So the architecture of Kubernetes. Basically, Kubernetes works with virtual machines. All of these boxes here, these are virtual machines. So Kubernetes has two planes. One we call the control plane. The second one we call the worker plane. So on the control plane, this is where the brain lies of Kubernetes. This is where all the magic happens. And under the worker node plane, this is where your workloads are running. This is where your containers would get deployed and they would be running. So this is a simple architecture. We call this a single master node because we only have one VM as a master on the control plane. That's it. So to interact with Kubernetes, we have two interfaces. One is called CLI. It's called kubectl. You can install it on your machine. Some Kubernetes clusters, it comes pre-shipped with something called a Kubernetes dashboard. And you have to, if that doesn't come pre-shipped, you have to manually install the UI. So working with those is like our main entry point of working with a Kubernetes cluster, like communicating with Kubernetes cluster and giving commands to it. Nobody, to be honest, Kubernetes dashboard is sort of deprecated. There are some security issues as well, so people don't usually use this much. People use the CLI. So CLI is the way to go. And it's very easy to use. I'll be showing that in the demo if the time permits. So in this scenario, I'm going to be speaking about a few components in Kubernetes, what makes Kubernetes tick or what makes Kubernetes work. In this particular example, we are talking about a highly available Kubernetes cluster, where as you can see, there are worker nodes here. In this scenario, the worker nodes directly connected to one master. But in this scenario, there's a load balancer in between where we have a highly available control plane where we have three masters here. And then I'm going to be talking about all the components in this Kubernetes cluster. So that would be in the next slide, but this is how a highly available Kubernetes cluster would look like. But as beginners, we don't expect you to build a highly available Kubernetes cluster or even single master cluster. What you can do is currently right now in the cloud, Google, AWS, Azure, they have this managed Kubernetes. So it's very easy for us. We can just go to the cloud, click a couple of buttons and create a cluster and everything is managed. We don't have to worry about this. But if your particular organization where you have data centers and you have the need to manually create a Kubernetes cluster, I think this is the architecture you need to have a look at to run it in production. I mean, for development purposes, yes, you can have a Kubernetes cluster like this, but yeah. So the components of Kubernetes. So in the master, we have actually four. The first one is etcd. So what etcd does is, etcd is the database of Kubernetes. And then there's something called API server. API server is the interface where we communicate with Kubernetes. So if I say Kubernetes run my Java application, I'm going to be talking to this API server. So when So when I tell this API server, Kubernetes run my Java application, what it's going to do is it's going to take that request and then it's going to save that request under etcd. It's going to store that data as a configuration saying that, okay, Nilesh needs to run a Java application. And these are the requirement specs for that Java application. That data is stored in etcd, and then this API server is going to talk to scheduler. So then it's going to ask the schedule, and the scheduler is going to decide where this Java application needs to, Java container needs to be run on these existing nodes. So after saving it, it's going to talk to the scheduler, and the schedulers would come back to the API server and say, all right, so this node 3 is the best place to run this particular container. It has enough resources, etc. Now API server then is going to save the data again, like under the HCD, saying that okay, now the container is updated, the workload. Now we have decided to schedule this on this particular node, node 3. And then what's going to happen, this is going to talk to kubelet in this particular node. Now this kubelet is the one that is responsible of spinning up containers and managing them in that particular node. So this API server is going to talk to the kubelet, and then it's going to tell the kubelet, okay, run this container on this, run this container. These are the specs for this container. So the kubelet is going to start, going to spin up the container. That's it. And then now, actually, when we talk about the life cycle, that's not it. Kubernetes needs to constantly keep track of these running containers. So there's this thing called controller manager. So once you run the controller manager spins into action, and it's going to talk to kubelet and always try to see what's the status of the container. Like it's going to ask the kubelet always, hey, what's happening with this container? Is it up? Is it down? What's up? So yeah, it's pretty annoying. If you look at that point of view, controller manager is pretty annoying to him. So controller manager keeps asking the questions, and then if the container is down, controller manager would know. Like for example, Java application might be frozen or something, or it might have a memory leak, or something happens. The application crashes. The controller manager would immediately know, because it keeps asking, it keeps track of the container. Then the controller manager would again save the data on etcd, and then it's going to either restart this container, or it's going to talk to the scheduler and run this container on a separate node. So either one of those could happen. It's just a basic scenario of how Kubernetes works. And one thing I didn't touch base is called a proxy. You can see that there's a proxy component in all of the nodes. So what proxy does is, so these VMs external to Kubernetes, in this external box, this is the network that the VMs are in. But however, inside Kubernetes, there's an internal network. This internal network is what allows us to do service discovery. Along with proxy, there's something called a code DNS as well. So it allows us to do service discovery, talk like this container to talk with this container, etc. All of that is what proxy is what enables us to do all of that. So that's that. So that's sort of a brief intro on how Kubernetes components work. I hope I wasn't too fast. And yeah, so we'll discuss more under the Q&A. Right. So on the next couple of sections, what I'm going to be talking about is key concepts, or like key resources. Like there's this thing called pod here. I mean, you probably don't know what it is. I mean, you must be already know if you're a bit familiar with Kubernetes. But yeah, so pod. Now we are talking about workloads running on Kubernetes, applications running on Kubernetes. So pod is the atomic unit in Kubernetes. It's not a container, it's a pod. Pod contains multiple containers. So one might be wondering, so why the hell is Kubernetes using this concept called pod as single atomic unit? Why couldn't it be just a container? Why couldn't container be the atomic unit? Then pod be something else. The reason being that to run a certain application, sometimes you need to have multiple containers to complete one business task. Like it's not like we would run a service backend here and a database here. No, not like that. Imagine a scenario where this is this is a process or an application that allows you to upload pictures, right? Uh, now when you now this is written in Java. Hypothetical, this is written in Java. So you upload the pictures and then you need to optimize this picture. Okay. To optimize this particular picture, say there's no Java library to optimize the picture hypothetically. Let's say there's a Python application to do that. So you can run that Python process as this. Yeah, this can be a sidecar. We call it a sidecar agent. So you can run that Python process here. So when we upload about a 50 megabyte or a 100 megabyte image for this container too, uh, it's going to save it somewhere. And then behind the scenes, this Python process or the Python container can access that image and optimize it to under, and then they convert it to a low bit image like 10 megabytes or something. It's just a random use case that I just thought of. Like that's the use case when we say running multiple containers in a pod. So pod is similar to a VM basically. So in a VM you can run multiple applications, etc. Likewise in a pod you can run multiple containers, and these containers would be sharing the storage, IP address. All of these things are shared here. So pod is a single atomic unit in Kubernetes. We work with pods, not containers. And one last thing, a pod in Kubernetes, we call it immutable, which means that a pod can either be created or deleted. You cannot edit a pod. Like this container can run on version 1, this container can run on version 2. You cannot change this version. You cannot edit it. You have to delete the pod and recreate the pod. Yeah. Then we have this thing called deployments. So what's deployments? So normally, when working with pod, we don't work with pods. Pods, as I said, is a single atomic unit, and it is we cannot delete it, or we cannot we can only create and delete. We cannot update it. So deployments allow us to manage these pods, because if we have around 100 pods, and if we want to update those 100 pods, we cannot personally go and delete those 100 pods again and create them manually again. That cannot happen. I mean, that's not feasible. That's where deployment comes in. So we would edit the deployment. We can edit a deployment. So when we edit a deployment, imagine that I have a pod running under Nginx version 1, and just imagine that it's a single container pod, and it has Nginx version 1 running. So I have that spec in the deployment, and deployment is going to spin up that pod. Now the second thing we do is I want to update that Nginx container into version 2. So what I'm going to do is I'm going to edit this deployment into Nginx version 2. Then what's going to happen is it's going to stop, it's going to delete these 2 pods, and then it's going to create 2 new pods with version 2. And then you see here, there's a box here saying that replica set v1, replica set v2, replica set v3. We don't work with replica sets. Replica sets are there. Behind the scenes, it's working, but we don't, when we write configurations for Kubernetes, we don't work much with replica sets. So what the duty behind replica set is, so the first scenario, I said I want to run Nginx v1. So when running it, replica set is sort of like a snapshot of the deployment at the moment. And using the replica set, these 2 pods are created of Nginx version 1. Now I'm going to update the deployment to version 2. Now the version 2 snapshot is there on this replica set, the configuration for the version 2. And then it's going to spin up 2 pods, and these 2 are going to die down. Now imagine this version 2 is bad. There's some problem, or you screwed up, I don't know, something happened. So now you want to roll back. Because this deployment is edited, how can we roll back? That is where the snapshot comes in. So you can roll back to earlier replica set, v1 snapshot, and then configuration, the previous configurations, the pods would start off with previous configuration. So that is how deployments, replica sets, and pods work. We normally don't work with replica sets. We write deployments when we do YAMLs, and using deployments we can do rollbacks, etc. One more thing, uh, these deployments, they are better suited for stateless applications. Uh, yeah. So that's that, and I'll tell you about what stateless applications are in a bit. So pods versus deployments versus service. Now that's a new thing. Uh, so when we talk about pods, uh, we have as a call coming. I don't know. Okay. Yeah. So when we have multiple pods here, now we would be creating pods. We would be deleting pods. Creating more pods, which means that these pods would have their own IP addresses. And then there should be a service. Like imagine there's another application running that is utilizing this particular application or these pods. There should be a single IP address that this particular application needs to talk to uh, in order to, I mean, it cannot constantly keep updating the IP addresses of all of these pods. Yeah. So that's where the service comes in. So deployment would have pods running, and then there's this another resource called service, and then we attach these pods to that service. Basically, this pods has this thing called labels, and then the service we say like all the pods that belong to this service would have the label app equals nginx. So every time we create a pod with the label app equals nginx, it is discoverable by this service. So whenever we send a request to this service, it's going to automatically send requests to all the pods, like on a round robin fashion. It's going to forward the traffic to the pod that belongs to this service that has the label app equals nginx. So that's how services normally work. So it allows service discovery. A quick touch base on rolling updates, how we do an update on Kubernetes when it comes to deployment. We have V1, these are two pods running on V1. And then when we do the update, the replica set is missing here. So we have V2 running here, and then it's going to slowly stop one pod of V1, and then it's going to put the traffic to V2. And then after that, this is healthy. Another V2 is updated. Another V2 is created to replace this. And once this is healthy, this is also deleted, and the traffic is now for V2. That is how rolling updates work. So first we have V1, V1, and then we are introducing a new one called V2. And once this V2 is healthy, one of these V1 pods will get deleted. And then another V2 is introduced and traffic is forwarded. And once that is also healthy, the old V1, another V1 would get deleted. And now we have a V2 update. So this is basically done. The rolling update is basically, we call it a zero downtime update. Basically, it just easily shifts in without you having to send emails to your employees saying there's a downtime, don't put any updates to the system, etc. And all of that is handled by Kubernetes with rolling updates. However, what it doesn't handle natively is advanced scenarios like canary or A/B testing, or shadow launchers, those things. To do that, there's this thing called service mesh. It's a whole different story. Maybe in a future webinar we can discuss about service meshes. So other resources, a brief intro. So as I said, the smallest component is Kubernetes. Atomic unit in Kubernetes is pods. So we have deployments. Deployments work with replica set. So there's few others. There's something called a stateful set. So when I say deployment, I say deployments are more aligned towards stateless applications like your backend Java application, the service side of things. They don't have a persistency layer. But imagine scenarios like databases. Databases have a persistency. It's not stateless. So databases require something like stateful set is there for applications like databases. And then there's this thing called job, where you want to run a container, you want to run a batch of job, which means that now deployments as stateful sets. These are mostly like, never-ending infinite processes. A process that would not end. That could be an HTTP server that keeps running, or a database service that keeps running. But job is a process that ends. So you would do a batch job or something and just ends at some point. So that's what a job is. Uh, and then cron job is a higher version of job, where you can schedule a job to run on an interval that you define, and that's that. So all of that, these affect the pod. Then daemon set. So what daemon set does is, sorry, if I were to uh, go up a bit, right? So there are three nodes here. So when we run a deployment, and when I say two pods to run on this deployment, one pod can get assigned to this node, another pod can get assigned to this node according to the uh, resources that are allocated in those nodes, available in those nodes. Sometimes the two pods can be deployed on the same node. It's a possibility, uh, unless you have this thing called affinity or anti-affinity configured. Both can be deployed on the same node. What daemon set does is, we would say, right, and I want to run Nginx as a daemon set. So the Nginx pod uh, would run on all the nodes. Like this node would have an Nginx pod, this node would have an Nginx pod, and this node would have an Nginx pod. So there's no scheduling when it comes to daemon sets. It's just one container, one pod running on all nodes. So each node would have a pod on that configuration. That's what we call as a daemon as well. So that is what a daemon set is. And then I already explained about services. And then there's this thing called horizontal pod autoscaler, which allows you to look at certain metrics of your pods, like the CPU or memory or incoming requests, and then you can tell horizontal pod autoscaler to automatically increase the number of replicas or decrease the number of replicas depending on the load or the metrics or the thresholds that you put in. There's another one that's not mentioned here called vertical pod autoscaler. It's going to look at the existing resources and requests we have given to this pod. Particularly hypothetical, let's say that we have given this pod 200 megabytes of RAM and one CPU. And hypothetical, let's say that that's not enough, or let's say that that's too much. The vertical pod autoscaler would automatically increase or decrease it according to the by looking at the previous data and by analyzing the current workloads. Uh, there's this thing called pod disruption budget, which makes sure that your pods would definitely, at least one pod would be running at all times. Like it's a bit advanced scenario. Ingress, where how your application be received or applied with through the internet. Like service allows you to expose your applications, but ingress is what allows you to handle the HTTP side of things, like let's say SSL, all of those things, domain mapping, all of those things are handled through ingress. And then there's volumes. So you can have config maps and secrets. If you want to have configuration files, you can store them as config maps or secrets. Or if you want to have volumes mounted to your container to persist some data, like take a database. So database, it has to be persistent. You need to store the data on a volume. So that's where volume comes in. So these are there are a lot more resources than this. Just a few. That's an overview here. So these are the brief intro to the resources. So after that, I'm going to do a demo. So before the demo, I think we can have a sort of a Q&A session. So far, because I've been talking for too long now. So do you have any questions?
Yes, so Nilesh, there are a few questions on the Q&A box. So in the meantime,
Yeah,
what I'm going to do is allow most of our participants to probably unmute in the meantime.
yeah,
So maybe I'll leave that for you to take over on the Q&A, some of the questions on the Q&A box now.
yeah, yeah, yeah. Right. So, so Jonathan, how does this go? I'm going to read one by one.
Yes, so probably you could take
Okay.
some of the relevant ones, which some of them I think you've already touched on, but
Yeah.
leave
Okay.
it to you.
Right. So I'm going to start. Okay. Okay. So before the demo, I'm gonna answer these, and then yeah. So the first question is how we choose best scaling method for microservices. Well, it depends on your requirements and your scenarios. Where mostly when it comes to scaling microservices, if it is stateless, the best method is to horizontally scale it, which allows you to uh, scale it horizontally dynamically and then scale it back down again, depending on the loads. But and also it would increase the availability scenario of your applications as well, rather than you manage one service, one app, one pod, and then scale it vertically. So it's always good to scale it horizontally. And the scenarios where vertical pod auto scaling comes into play is that sometimes you need to identify exactly how much CPU and memory you need to give for one of these services. You need to understand that. You need to find it out. So that's where vertical pod autoscaler comes into the benefit, to be honest. So running a vertical pod autoscaler with there's this thing called recommender system. So using the recommender system, you can very easily figure out running a pod. You can see like what's the required or appropriate amount of CPU and memory required to run a particular container. Because otherwise, how would you know, right? You can't. Otherwise, you have to run explicit tests on load tests, etc., just to find out how much CPU and memory are needed to run your application. It's not straightforward. So I think those things work hand in hand. But I would say horizontal scaling is the best method for your microservices. All right. And the second question, so every 10, yeah, I'll be sending this presentation to Jonathan. So I think Jonathan already has it. So you can get the presentation slide deck. Another person says, is it one microservice per container? I mean, one microservice in one container. Definitely one microservice in one container, but depending on the use case, you can have two microservices running on a single pod. But normally it's one microservice per pod, and then you would have this thing called sidecar containers that would have additional functionality or features uh, would allow your microservice to increase expand its value. So I think Dinushanka has answered that correctly. So why we need orchestration? Is it to on off containers, or is it for something else? What is the uses of orchestration? I think I answered this on the slide, why orchestrators. Like just to recap again, if you didn't understand it. So when we have multiple thousands of containers running, a single human uh, cannot usually manage these containers through a CLI, a Docker CLI or whatever. You cannot do that. It's extremely hard. If you're running one container or two container, you can easily spin it up. You can manage it on your own. But thousands of containers, that's extremely hard. It's not feasible. That's one of the reasons why we need orchestrators. Other than that, uh, to manage, it's not to on off containers, mostly manage these containers. Like, so we have a cluster of virtual machines. Like when you're running microservice system, you won't be deploying it on one virtual machine. You would have a cluster of virtual machines. And in the cloud, you have availability zones. You have bunch of VMs in one availability zone, another bunch of VMs in another availability zone. So now you need to make uh, DR solutions, redundancy solutions, etc. So running all of those manually using Docker CLI is going to be hugely cumbersome. That is where an orchestrator would come in. Basically, we would spin up the VMs, we would dedicate those VMs to the orchestrator and give orchestrator the captain role. So, and then we would just tell orchestrator, run my application. And then orchestrator is going to decide where the application is going to run. We are going to tell orchestrator to scale my application, and the orchestrator is going to scale it. So it's basically going to manage your container. It's going to manage your workloads. That's it. Yeah. I hope that answers your clarifies. I think yeah, I already said that. Asiri. Asiri is a beginner. What will happen if one container got vulnerable? Is there a security thing to detect it? Yes, good question. So the problem with containers, if I were to go back on my slides, was it here? Right. So I hope you can see. Um, so these containers, these are running processes. These are processes, and these processes are talking with host operating system, which means it's talking through the syscalls of the host operating system. So if the host operating system has a vulnerability or a security vulnerability or something, this app A, I mean, it can exploit it and then attack B, C, D, E, and F. And that's a possibility. You can do that. So that is why usually we don't run multi-tenant systems under Docker. Like I won't run my app as app A here and your app as app B here on the single VM. It is normally towards enterprise, right? So this enterprise or my company would be running the company apps here. So it's a single tenant at the end of the day. So it's mostly towards single tenancy. And there are things like there's this thing called container sandboxing, which allows you to sort of there's this called AWS Firecracker is there, gvisor, Kata containers. So there are few solutions that allows us to sort of avoid that scenario and have multi tenancy with sandboxing. And also when it comes to tools, there's this thing called sysdig. Google it, sysdig Falcon. So using sysdig Falcon, we can see what are the containers running, what level of permissions there are for these container processes, the root, like whether they are trying to access root, whether they are doing something fishy, even they are doing Bitcoin mining, whatever those things. Sysdig Falcon, it's open source. What is the best practice? One container for a pod or multi containers in a pod? One container for a pod, like one microservice for a pod, but definitely there would be sidecar containers. Like there's this whole thing called service meshes, which we can touch base later on a later webinar. So what sidecars allows you to do is it just allows you to expand the functionality of the existing container, like what I said with my example with Java application uploading 50 megabytes of images and a Python service running behind the scenes to optimize it as has the Java application saves the image. So stuff like that, we call that a sidecar. It just enables or like extends the functionality of the main service. That's what we do. Yasiru has said, if I add new nodes, are these daemons that get installed? Yes, I think Kasun has answered. Yes, it will. That's the whole point of daemon set. 1 plus 60. How is network security enforced among containers? For instance, if I would only want app server container to talk to the DB server container. Yes, so there's this thing called network policies, but it would depend on the network CNI plugin you use, as Kasun said. There's, I think, commonly a lot of people are using this CNI called Flannel. So Flannel doesn't have network policy capability. Like if you want network policy capability, you need to go with something like Calico. So when you have Calico or something running, you can have network policies and like there's this thing called namespaces. So you can run your applications on one namespace and then you can run your database or whatever in another namespace. And then you can add network policies there saying that, okay, so this database network namespace can only receive requests from the application namespace. You can configure network policies very easily like that. 1 plus 60 has a lot of questions. I often hear the term Helm with Kubernetes. Can you please touch base on this briefly, why it's needed? Okay, again, a good question. I think if you're giving away gifts, I think he deserves one because he's asking good questions. Right, you see, to run an application, So if you're running your own application, that is fine, right? You would have your YAMLs, you would have your configurations, that's all cool. But imagine you are shipping your application to others. Like imagine you are building something like a MySQL. Okay. Now you're shipping it because other people would be using it. It's not a SaaS shipping it, other people to use it on their Kubernetes clusters. Now, your YAMLs, the way you have defined it is not the way other people would want to run your MySQL. You might want to make some configuration changes. Like, for example, run your application resources on a different namespace, something like that. Or maybe that particular person who's running your application, the application you built, you ship, they want to run 5 replica sets instead of the 3 replica sets that you have defined. So Helm is sort of a way where we can attach all of these configuration, bundle all of these configurations as one, and then we can, it's sort of like a templating engine. So with that, we can add configurations. So right, when we do it, like say your application is called app one. I'm sorry, I couldn't think of a better name. So if you are shipping your app one, you can just say helm install app one, and then you can add value overrides. You can define value overrides on the application. You can say, right, so the user who's installing my application can change the number of replicas in the stateful set. So when you install it using Helm, the person who's installing it can change the configuration according to their needs. So that's where Helm is there. So Helm usually allows us to package your application. Like an application would have stateful set, autoscaler, config map, a lot of these YAMLs. It would allow us to package those things together, and also allows us to make it like a template so that users can sort of override certain configurations for their according to their requirement. I hope that Oshan, can we SSH into a container running on a pod similar to how we normally? Yes, you can. You can. However, you have to make sure that particular container has a bash or a sh shell. If the container doesn't have a shell, you cannot SSH into it. You have to make sure the container has a shell. Some containers don't have a shell. Yasiru, let us know what is the best way to backup etcd and restore. Right. So the best way to backup and restore, you have to have a look at Rancher RKE. So you see Rancher RKE, it's very easy to backup and restore an etcd cluster. You can even push the backup of the etcd into a cloud S3 bucket very easily. I mean, if you were to do it manually, you just have to, either write a cron job on Kubernetes, which would call connect to the etcd cluster and get a backup, and then you can write your own shell script to push it to whatever the S3 bucket or wherever you want to do, and then the restore, you have to just restore is when something goes pretty shit, right? So in that scenario, you can simply SSH into the etcd cluster itself, one of the etcd containers, and then you can do a restore using the backup. I hope that answers your question. How microservices troubleshoot going inside pods. So Kubernetes has logs. So all of these containers, etc., they have logs running in. So you can ideally, the first step is debugging using logs. Other than that, I spoke about service meshes. I think we have to touch base this on a future webinar. So we have tracing. There are a lot of add-ons that we can do on Kubernetes with service meshes. So tracing and other stuff. So that would help us to do troubleshoot. Otherwise, yes, I understand your problem. If you have like hundreds of microservices and then all of them talking to each other, I mean, forget about Kubernetes. In a microservice architecture, that's going to be cumbersome. That's going to be very, very challenging for you to do debugs. But with service meshes, it makes things relatively easy. So we'll touch base that in the future webinar. Is serverless programming backed by cloud providers going to eliminate the need of containers in future? Actually not. So I believe you are talking about Lambda or cloud functions. They are good for, like, we call them nano services, to be honest. Like, you do it and be done with it. Like, you can run HTTP servers too, but like behind the scenes, if you look at it, they are also using containers, right? Your application is running as a container and then it spins out. And you don't see that. You just upload the code for these Lambda and Cloud functions, and behind the scenes, that's what happens most of these cases. Google App Engine, containers running behind the scenes. So I don't think it's going to eliminate the need of containers. Containers will live on. And with Kubernetes, what happens is that it's cloud agnostic. Like, if all of your systems are running on Lambda, what all the, like, Cognite on AWS, etc., you're running all of these things on AWS services. And one day AWS decides that it's gonna, like hypothetically, let's say that Jeff Bezos is bankrupt and he wants to earn a quick buck. So Jeff Bezos would increase the pricing on AWS, and then all of a sudden your bank account is empty. And then it would be hard for you to migrate to Google Cloud or another cloud, because you have this tight vendor lock-in with AWS by using these services. I'm not just talking about AWS. I mean, other cloud providers do this too. We call that vendor lock-in. But with Kubernetes, introduction of Kubernetes, everything is cloud agnostic now. You can run it the same way you run AWS, Google Cloud, everywhere it's the same. And then even on premises, on your data centers, you can run it the same way as cloud, and you can even utilize all the services that cloud provides, like auto scaling, etc., within Kubernetes. So yes, so my answer for OnePlus 60 is that it's not going to eliminate containers in the future. In fact, containers are what enables the serverless programming, etc. Can please share this webinar after it's finished? All right. So yeah, I think that's for Jonathan. You mentioned Nomad by HashiCorp, also used for what are the scenarios where Nomad is better than K8? Excellent question. So hypothetically, let's say that Nomad is like a lighter version of Kubernetes. Yeah. So to run Kubernetes, you require, that's a sort of requirements. You need to have a control plane, you need to have a worker plane, and on the control plane, you need to run etcd. That's the master node needs to have 2 CPU and at least 2 or 4 GB of RAM, and on top of that, the worker nodes need to have a certain amount of CPU to run the components, cluster components that I explained to you guys. So Nomad is less heavy. Like, if you don't have thousands of microservices, if you don't have a bigger scenario, you just want to run your container. You just want to run a couple of containers and be done with it on a single container, a single VM, or a couple of VMs. That's it. You don't have huge expectations. You don't want those things. So Nomad is a pretty good solution for a scenario like that. For simple people to just run a container, just run container and just manage the container, Nomad is a pretty simple solution. I mean, you can read about the case studies when it comes to where to use Nomad and where to use K8. Like, Nomad has a good case study link in the documentation. You can see what users say about Nomad versus Kubernetes. But yeah, right. And Asir Hevage says thank you. Yeah, no worries. So I think we are at 7:10 right now. Shall I skip the demo? Do you still need the demo?
I think we can take 5 minutes, Nilesh, and quickly run through your demo. I think
Right,
no
cool.
problem. Yeah.
All right. Right. It's not a big deal. Right, so let's see which cluster I'm on. So in this demo, what I'm going to do is I'm going to just run an Nginx image, and I'm just going to create a service, and yeah, I'm just going to create a deployment and a service, and then I'm going to show you how to run it. Okay. I'm just going to do I'm just going to explain you how to use kubectl as well. Hope everybody can see my screen. Yeah, and I'm one of those people who use a white background on my editors. Yeah, I'm going to hell. Yeah. Okay. So to run a deployment, I'm just gonna do a small thing. So if I were to run a pod, how I would run it is kubectl run. I would say a name to the pod. I would say nginx, and I'm just gonna say the image is gonna be nginx, and then I'm gonna say I want to run this as a pod. So I'm gonna pass the flag restart equals never, and I don't want this to be executed on my cluster. I just want to dry run this. So I'm just gonna type dry run just to show you guys. And then I want the output of the dry run to be output as a YAML because I want to save this configuration so that I can change it the way I want. So I'm gonna dash o YAML here. Right, run it. There you go. I got this is what the Kubernetes configuration is. So I'm just gonna put this into pod.yaml. Right. You can see here that this has an API version. This is the Kubernetes spec. So it's always advisable for us to use these YAMLs. Otherwise, I mean, if something happens, what are you going to do? You don't have the configuration. If you do it on the go, you don't know what to do after that, right? So I'm just going to create a namespace. I'm going to say kubeNS, kubectl create ns webinar. And I use this tool called kubeNS, which allows me to easily switch back and forth with these namespaces rather than I have to pass the namespace flag every time. So I can just add the namespace here, also saying namespace webinar. Right. So this is a pod. You can see API version v1 kind pod, and the spec part is where everything is interesting. You can see there's an image here, so you can see container. So you can add multiple containers. You can do it like this. You can add another image here, and if you're going to export a port, you can say can't remember how to expose a port. So if you don't remember how to, now I know that you can put ports here, but I don't know exactly what config to put here. And the Kubernetes documentation is really confusing. So in order to do that, there's this uh, way you can do it called kubectl explain. I'm just going to do kubectl explain. So I want to see what are the options there are for containers. In order to do that, the resource is pod. So I'm going to say pod dot under pod, I want to check out spec. So I'm going to say spec dot, because I want to see all the resources in containers. I'm going to go with containers, right? So I'm going to do kubectl explain pod dot spec dot containers. So when I go here, you can see that I got a bunch of fields that are there available for containers. So I'm just going to go down. This is on alphabetical order. There you go. You have something called ports. So I know what to put here. It's ports. Now, ports is an array. It says object array, which means that this this is an array. Now, I don't know what to put inside these ports because it's an object. It's not an integer where I can just type 88 or something. I can't do that. So it's an object. So I need to find out what's there on ports. Similarly, explain pod.spec.containers, I would say ports. You can see now it has container port, host type, a couple of things. I'm just going to use container port here. I'll just say container port will be 80. Will be 80. Yeah, that is how you use kubectl explain to find out what are the options you can put on these configurations. Pretty cool. Yeah. Okay. What I'm gonna do now is I'm gonna just apply this. I'm gonna kubectl apply -f pod.yaml pod nginx created. We can view it kubectl get pods sorry, not PIDs. I'm sorry. Clumsy fingers, butterfingers. So yeah, nginx 1 out of 1 running. So 1 out of 1 here means 1 out of 1 containers are running because we only configured 1 container here. Now imagine that we want to update this pod. We want to update this into the latest version of nginx, hypothetically, let's say like that. Now if I do kubectl apply f this pod.yaml, will it work? I don't think so. It did actually, I'm sorry. All right. But in normal cases, it normally doesn't work. Like if I were to say 8080 or something like that, yeah, it's gonna give an error. You cannot update it. So the reason why nginx colon latest worked was because if I type just nginx, the latest tag is also comes as automatically. It's a given. If I say v1 or something, I don't think it should work. Yeah, there you go. So okay. So in order to update it, what we need to do is we have to delete the pod. And then we have to manually create the pod again. It's going to be cumbersome. Now you have multiple thousands of pods. You cannot go around and manually creating and deleting pods. That's where deployments come in. So kubectl run nginx. Now this is the previous command that I ran. So instead of running never, I'm going to type some run called always. Now running restart always would generate a spec for a deployment. That's the only change I'm doing. So I'm going to say deployment.yml. There you go. So now if I were to show these two together, if I take myself to the bottom of the screen, you can see that this is a bit different, but it's somewhat the same, because you see here under 19 spec containers, all of this is somewhat similar to one here, because that's the same thing, the containers here. So I can run, put these two also here. Right. Okay. So under replicas, we can under deployment, we can say that, right. So the replicas is 2. I can run. I can scale it up and scale it down as I want it very easily. So all of that is very simple. I'm going to apply this here, apply as deployment.yml. Right. So deployments app nginx created. So now I can just check my deployment, kubectl get deploy to check deployments. You can see that it's 2 out of 2 running. So 2 out of 2 running means that I said there are 2 replicas in the deployment. So that's what we mean by 2 out of 2. So I can say kubectl get pods. I would see the two nginx pods running here. The next thing I want to do is I want to expose this. Now, funny thing, right? Kubectl get pods -o -o wide. So if you look here, you can see the IP addresses for these 2 pods. Now I'm going to run an update here. I'm going to say this one. I'm going to give a resource here. I'm going to say requests. So Kubernetes has resources, requests versus limits. So request is basically what we do so that scheduler would know that Kubernetes can, or like how much resources it requires to run this particular application. So I'm just going to say I want CPU to be 100 milli-CPU and memory to be, I think 50 MB is enough. We call it MI, not MB here. So I'm just going to apply this again. So it configured. If I do get pods now, you can, no, hold on a sec. Now you can see that a new one. Now the rolling update is happening. So you can see the IP is changing. So one is terminating, and yeah, and then you can do again. Now, yeah, now these are 2 different IPs. Earlier we had these 2. Now these 2 IPs are different. Now, if you are reaching for these pods, if you want to talk to nginx, I mean, because these IP addresses are dynamic, it's going to be hard for you to figure it out. You cannot hard code it. What can you do? That's where services come in. So you can do kubectl expose, yeah, expose deploy. I'm going to say my deployment name is nginx, and my port is 80, the service port, and the target port is also 80. And then I'm just going to do a dry run. and dash OYAML just to get the output, and then I would say service.yaml. Right. So here I have service.yaml. Now look, if I do kubectl get pods show labels. Now all these pods have labels, okay? So you can see that this pod label has something called run equals nginx, run equals nginx. And you can see that in this particular service under spec, you have the port. The service port is 80, protocol is TCP, target port. Target port is the pod that is targeted towards this the service forwarding traffic to these pods. Now these pods could be running on 80, 80 or something else. In this scenario, we have 80, so that's why it's 80 here. And then there's something called selector. So it's going to forward traffic to all the pods that have the label run:nginx. This, all the pods that have run equals nginx is how the service discovery is happening. That's how it forwards the traffic. So I'm just going to apply this. Kubectl apply -f service.yaml. Right, so it's created. I can do kubectl get svc. And there are multiple service types. There's node port, there's load balance, etc. This is not a Kubernetes class, it's a demo. So yeah, okay. I'm just gonna forward this kubectl port forward svc nginx. I'm gonna forward 8080, like 8080 would be the port on my computer I want to bind it to. The port of the service is 80. So I'm just gonna run it like that. I'm just gonna go do a curl here. Localhost 8080. And I have nginx. I can show it here also. Localhost. I'm scared to type on my browser because I don't know what kind of links that would pop up. I don't use it incognito. So yeah, okay, there you go. So this is forwarding proxying straight from the cluster that's running. The cluster is running in GKE. So that's it. And this is just a basic demo of deployment pod and service, which I explained. But to run a real application, there are more things that you need to do, like all of these things. You need to have config maps, secrets, ingresses, a lot of things. And like if you're interested, right? I work in a company called Platform Cloud, where so I see this problem. So that this is a problem I see, and I have architected a product called Platform Cloud, which allows users with zero knowledge in Kubernetes to quickly get deploy their applications on Kubernetes. Like it's basically like very easy setting up an app. It's very easy to set up your application. Just demo 5 or something. And then can see 8080. And then set up a CI/CD. All of these things in Kubernetes is, I mean, you can do it, but it's hard. A lot of there's a learning curve. So you can connect your GitHub all under about 2 minutes or so. Yeah, so you can say demo. Like the main reason I architected this product is to ease in people for Kubernetes, for easily use Kubernetes, and just not worry about writing configurations or YAMLs on Kubernetes and just focus on your application code. And CI/CD and all of those things are fairly simple. Yes, I can create a CI/CD pipeline like this very easily. Run trigger. I'm just gonna do master. Yeah, so other than that, you can mount You can add config files to this one, so etc. etc. Very easily you can mount configs. So all of these stuff are generated for your application behind the scenes with a simple UI, so you don't have to worry about writing or managing those YAMLs at all. So you can add mount configurations to your application, you can mount volumes, you can check out logs, you can set up ingress, you can set up SSL, all just automatic for you. I'll just show a created application that I did earlier today. I can't remember. So let's just go ahead with the demo one we have. Yeah, so that's basically it. Do you have any questions? That's my demo.
I think in the interest of time, probably what I'll do is share Nilesh's connectivity as well as my email address is around. We'll be sharing this presentation for those who are asking. And yeah, Nilesh, go ahead.
So a couple of final thoughts before we closing down. As I said, Kubernetes is hard. You need a lot of practice. Managing clusters and running workloads are two different fields when it comes to Kubernetes. Managing clusters is extremely difficult, whereas running workloads is somewhat okay. So that's where cloud providers come in and gives you these clusters they manage and allows you to just run your workloads. And yeah, so don't go into production with your company if you don't know how to set up security, networking, ingress services, or if you're not a pro in Kubernetes, don't go to production without being a pro. That's one advice, because there are a lot of people I know who went to production with Kubernetes with little knowledge. They just thought that they'd learn it on the way, but they didn't. And some clusters got attacked, and there were a lot of vulnerabilities and a lot of issues. So I personally don't recommend that. And also, I personally don't recommend you to run databases like Postgres, MySQL on Kubernetes. Uh, that's my personal recommendation. Some people say to run it, some people say not to. But there are cloud native databases like Vitess, etc., that allows you to run sharded databases on Kubernetes, like MySQL. Vitess is of MySQL. There's CockroachDB, Mongo can be run. So stuff like that can be run on Kubernetes. So have a look at those. And also, Kubernetes doesn't solve all your problems. Okay, uh, for monoliths, Kubernetes is mostly towards microservices. If you have a big ERP system as a monolith, maybe Kubernetes isn't the solution for you. You have to sort of weigh down your pros and cons to see whether you should use Kubernetes or not. But if it's microservices, definitely Kubernetes is will help you a lot. And as next steps, if you are beginners, so Katacoda has excellent tutorials, practical tutorials for Kubernetes. I'd like you to head over there. If you want to try out Kubernetes, you can easily go into the cloud and go into this $300 or whatever, the free tier they are giving in, and set up a cluster and try there. Or use Minikube, MicroK, Multipass, or something like that to run Kubernetes on your local machine. You can do that. Start reading Kubernetes docs. They have good tutorials. So start reading them, and then reach out in the community if you have more questions. There's Kubernetes Sri Lanka, there's DevOps Sri Lanka, Explore Dev community, Azure Squad. There are a lot of communities there who are working with who are promoting Kubernetes and helping the community. So yeah, and you can reach out to me too. I think the links are there. You can reach out to me on LinkedIn and Medium and Twitter. Yeah. So I think we already had the Q&A. Thank you.
Thanks, Nilesh, and thank you all for joining this session. We'll be back with another session with more focused on microservices, but I also think that given the questions, Nilesh, at some point, we'd like to do a part 2 of this with a little bit more on the focus on the Q&A, and possibly even more time for Q&A in our next Kubernetes session. So that's going to be probably in August, but end of July, don't forget, we'll be having the session on microservices soon as well. So thanks everyone for joining in, and like we said, Nilesh's details are on and my email addresses as well. So if you need any questions or suggestions, do please send it across to us. So big thank you to Nilesh for taking his time being here. Great session, Nilesh. Thanks a lot, and thank you everyone for joining. So good night.
Thank you.